Thanks for coming to my presentation. My name is Ray Weil. I'm a professor of soil science at the University of Maryland in the Department of Environmental Science and Technology. And today I'd like to present some data that my students and I have been working on with regard to cover crops and their ability to enhance macro and micronutrient cycling. When it comes to nutrients and cover crops, it seems nearly all of the attention has been paid to nitrogen. And so we thought we could maybe give some of the other nutrients their due and expand the value added use of cover crops. So to do this, we utilized an experiment that we had ongoing that involved a 12 species cover crop mix with four brassica species, 4 legume species, and 4 grass species. And these were planted on 3 different dates. They were interseeded using a high boy air seeder into corn in early July and in early August, and then also drilled after harvest in late September. What you see in the pictures here are the early drilled, the early interseeded cover that was the seeds were broadcast in around the 1st of July, but they really didn't germinate until the end of July when we got some rainfall. This is what they look like in mid-August, in a few weeks later in September, and after harvest in October. So this experiment was done on 2 soils, very sandy soil, almost a loamy sand, and a silt loam with much more clay in the profile. And it was also, interseeding was done with 3 different corn hybrids, and the design included a no cover crop control. So the methods were pretty standard for cover crop research. We measured the biomass using 3 quadrants per plot. This was done both in fall, late fall, in early December, which was sort of the maximum growth for fall before the radishes, which normally winter kill. They winter killed a few weeks later. And then again, we measured the biomass and collected samples in late May, just before termination in early June, when the cover crops were in full flower. The tissue was then prepared and analyzed, digested and analyzed by ICP for all the main macro and micronutrients, and for using LECO dry combustion for the nitrogen analysis. We also took soil samples about 6 weeks after the termination of the cover crops. So in July of the following year, when the corn that had been planted into the cover crop was in the V5 to V6 stage, we took composite soil samples and ran MELIC 3 extractions on these, and we're going to report the data for the 0 to 10 centimeter layer. So here is the weather that we encountered during this time and kind of a timeline of what was done. So it was a pretty good rainfall year, pretty steady accumulation of rainfall, except for this dry period, which I mentioned. The initial interseeding sat ungerminated for about 3 weeks or so. The next interseeding took place in August, and then we also drilled after harvest a little bit earlier in the sandy field than in the silty field. And then in spring, late spring, we terminated these early June, and then in July took soil samples. So that's the timeline of what we did. So let's get to some of the data. First, we'll look at the level of biomass produced, and I'm going to report this by family because in the fall, without flowers, it was pretty impossible to separate out individual species, but we could easily separate them by family. So the above ground biomass of the cover crop clearly did better with the earlier interseeding, the bigger head start. And the later one, the planting, the less the biomass, also distinctly less legume in the mix, and perhaps a little more of the grasses in the mix. So the early planting achieved about 1.6, 1.7 megagrams of dry matter per hectare in the fall. In the spring, we were able to separate out individual species. So these are kind of color-coded. The reds and yellow is the grasses. The green shades are the legumes, and the blue shades are the brassicas. And again, you can see that the earlier interseeding did much better. We increased the biomass to about 3.3 or so on average between the sites and replications. And the cover crop that was drilled after corn harvest in September never did catch up to the interseeded ones. These are the 11 species that remained. The radish was one of the three brassicas, kale, rape, and turnip. The radish was dead and gone by now. The legumes were hairy vetch, 3 types of clover, and the grasses were ryegrass, cereal rye, triticale, and wheat. So let's look at some of the nutrient contents then. Starting in the fall, we're talking about vegetative growth. There were distinct patterns amongst the families. Of course, the legumes, as you'd expect, were highest in nitrogen. The brassicas were second, but the legumes were significantly higher than the others. And the brassicas were significantly higher in both sulfur and phosphorus than the other families. So if you're trying to recycle sulfur and bring sulfur up from deep layers and increase sulfur fertility, the brassicas are probably your best bet for that, and also for phosphorus. For some of the cations and boron, potassium was distinctly higher in the brassicas in the vegetative state. We had some very high individual analyses. And the calcium also was quite high in the brassicas and in the legumes, much higher than in the grasses. Boron was distinctly higher in the 2 dicot families than in the monocot families. So that also would be a way of recycling that boron that also pretty easily leaches down in the profile. We also looked at some ratios of nutrients because this is often helpful in diagnosing fertility problems and status. And so the nitrogen to sulfur ratio showed distinct differences amongst the families. A very tight ratio in the brassicas because they're high in sulfur and not that high in nitrogen. And so they have a lot of sulfur compounds that are not part of the protein. So the two aren't as tied together. The grasses around 10 and the legumes are around 15. So the legumes had the highest ratio there. For calcium, the calcium to magnesium ratio was distinctly higher in the brassicas. The potassium to magnesium ratio was distinctly lower in the legumes, because the legumes do have difficulty competing and taking up potassium. And the sulfur to boron ratio was distinctly higher in the grasses. But moving on to the spring harvest, which was in full flower now, mature plants in full flower. Again, of course, the nitrogen was highest in the legume. That maintained a high level. Nitrogen was a bit lower and had gone down from the fall in the other 2 families. The advantage of the brassicas for sulfur and phosphorus was still there, but not as pronounced as it was in the fall. So killing the brassicas earlier, if you have sufficient biomasses, you've probably already accumulated the sulfur and the phosphorus that you're going to accumulate, and further growth is probably just diluting it. For potassium, the differences pretty much disappeared. They were all about the same, about 2.5% in the tissue. Calcium, they're still much lower in the grasses, and boron was still much lower in the grasses in the spring. Looking at some of the ratios, the patterns were similar, whether it was the vegetative tissue in the fall or this tissue that was in flower, the whole plant that was in flower in the spring. The pattern was very similar, only the nitrogen to sulfur ratio had even gone higher in the legumes. The calcium was still a little bit lower, the calcium to magnesium ratio in the grass, and distinctly higher in potassium magnesium ratio in the grasses, and also in the sulfur to boron ratio. So that seemed to be pretty characteristic of the grass family. I've been presenting the data on the averages for the family. We did in the spring have individual species separated out, and so I wanted to show you what this individual data looked like. So this is just as an example, the sulfur in the dry matter separated by individual species and by the two soils, the very sandy soil, the dark bars, and the silt loam are the lighter bars. And you can see why it's pretty justified to think of these as families of plants rather than individual species. All the grasses were very similar in sulfur, with very little effect of the two fields showing up. Fair amount of variability here, nothing significantly different. The legumes were, as a group, a little bit higher in sulfur, and also a lot of variability, so no real differences among the legume species. A little bit, this was just barely significant, but I wouldn't put too much emphasis on this effect of the soil on this particular species of clover. The brassicas were distinctly higher than the others. Again, there appeared to be some site effect of the soil, but with the high variability, there were some very weak interactions in there. So I think overall, it's justified to look at the family to simplify things. When we looked at the ratios, it even became more clear that that was the case. So for instance, the nitrogen to sulfur ratio was very uniform within the grasses at around 9 or 10, much higher in the legumes, around 18, and much lower in the brassicas for all the brassicas at around 5 or so. So I think it's probably practical to think of cover crops in terms of the family that they belong to when we're trying to manage particular nutrients. We did find some significant effects on the MELIC-3 soil tests taken after these cover crops had had a chance to do some decomposition, which was a little bit surprising. So this is the effect on soil tests of a single cover crop compared to where there was no cover crop, and there were weeds. We didn't control the weeds over winter, but the weed biomass, as you saw, was quite a bit smaller. And also the weeds, we know from other work, at least the weeds we have in Maryland, we never find that they go very deep and recycle nutrients from very deep in the soil, whereas many of these cover crops have deep roots. But anyway, the sulfur, MELIC sulfur, increased a little bit. It was significant, but small. I'm not sure how meaningful that is. But phosphorus more than doubled. And this was across the board for this mixture, because of course we can't separate out the families since they were grown as a mixture. And this certainly indicates that it has implications for phosphorus fertility. I think if you're producing a good cover crop like this, you probably should not be applying phosphorus fertilizer to the following crop. That cover crop, if it has this kind of biomass and phosphorus content, is recycling enough, at least in the near term, that you probably don't need to be applying additional phosphorus, or certainly nothing beyond a starter. Some of the micronutrients were also significantly affected. Copper, zinc, and manganese were all increased quite dramatically with the cover crop. This is probably partly due to cycling of the actual nutrient, but also might be due to the increase of organic matter and the decomposing material aiding in the chelation and solubilization of existing micronutrients there. But the calcium also increased significantly from 220 to 300, almost 340. So that involves quite a bit of calcium per hectare of land. So we definitely got to change the soil test levels. So I think we can conclude that if we manage cover crops well, we plant them early, do what's necessary, and allow them to grow long by planting green and giving them a full growing season, that they can produce significant biomass and cycle, bring up and contribute significant amounts of nutrients, economically important amounts. That this captured nutrients from deep below and bringing it up to the surface can concentrate them sufficiently at the surface to increase soil test and presumably availability to the following crop. So these characteristics of the families may allow us to use cover crops as a tool, selecting cover crops from particular families to address particular nutrient deficiencies that we might have. So thank you very much for your attention.